Okay. Okay, it's my big pleasure to have a new ZAG seminar talk, and my big pleasure to introduce Artan Sheshmani from Harvard. And Artan will talk about Atiyah class and sheaf counting on Calabi Yau fourfolds.
Thanks, Vanya, and thanks for having me in your amazing seminar. It's truly an honor. I've been following these amazing talks every week, and I think it's one of the best things that happened to algebraic geometry. I feel like the quality of algebraic geometry seminars improved beyond Corona. So, because now we are listening to amazing talks all over the world. Okay, so this is joint work, as I have mentioned in the title, with Professor Diakonescu and Professor Artan Yau. And so let me stop the video because you will be looking at the ceiling otherwise, because I'm going to write on my iPad. So I stop it and then I start. So I would like to also say that some of these things, especially the detail I will give about Atiyah classes, might be very preliminary for experts, so I apologize in advance. But because there might be people who are interested in some of the ingredients, I will give some description of the building blocks of the problem that I'm going to talk about. So let's talk about first Atiyah class. Without any further delay, let's set up some geometric situation. So let X be a smooth projective variety. So be a projective, smooth algebraic variety. And let us look at embedding of X inside its a diagonal embedding of X. So let X be diagonally embedded inside X times X. This is the diagonal embedding. We can look at, in this embedding, we can look at infinitesimal neighborhood. So infinitesimal neighborhood of X in X cross X. That's very easy to describe. So this diagonal embedding will have an ideal. So basically, sheaf theoretically, you can say that there is a short exact sequence. The structure sheaf of X times X goes to here. And then there is an ideal associated to the embedding. Let's call it ideal J of delta. And so now you can easily, from this short exact sequence, see that, of course, O of X is isomorphic to OX cross X times over modulo image of J of delta in OX cross X. But then infinitesimal first order neighborhood of X, which I'm going to times, or you can call it O delta also, the diagonal of X inside there. And then you can actually define first order neighborhood of diagonal, and this is going to be O of X cross X J delta square. So this is the structure sheaf of first order neighborhood of delta in X cross X, of course. Okay, so by this definition, as you can see, these modules are all made of taking quotients by ideal and ideal square J delta. So it is clear that I can have a short exact sequence made of these, which is O of 2 delta goes to O of delta. And then, so this is O X cross X divided by J. This is O X cross X divided by J squared. Of course, what is the kernel of this thing? This would be obviously J mod J squared. And this J mod J squared by, EGA or Hartshorne or anything you would like, it is the conormal sheaf of delta in X cross X. This is what it is. Okay, so this is that. Now, I would like to start with the coherent sheaf. So let F be some coherent sheaf on X. In fact, we are going to generalize it. So it could also be, or F could be an element of bounded derived category of X. So it could be a complex of sheaves, and the construction is really the same. So I would like to define Atiyah class of F. So goal is to define what I'm going to call Atiyah class. Atiyah class of F, class of this coherent sheaf F. Okay, so how do I define it? Let us look at this picture. So there is this X cross X, and then there are two obvious projection maps onto each factor of X. Let's call them P1 and P2. And so we can, so let's call this, okay, so we have this O of 2 delta goes to O of delta. Let's call this short exact sequence, something short exact sequence A, for instance. What we can do is we can, F is, let's say, you know, in here, abelian, in some element of abelian category of X. So we can pull back F. So we can tensor short exact sequence A with pullback of F, P2 upper star of F. Okay, so if we do that, what do we get? We will get the usual thing. So P2 upper star of F, these are all locally free sheaves. So O of 2 delta, P2 upper star of F, tensor O of delta, and P2 upper star of F tensor with J mod J squared. All of these sheaves are really locally free. So tensor product would be an exact functor, really, in this situation. So, okay, then we can project, now project via pushing forward along the other projection map. Okay, so P1, and let's see what we will get. Well, because F is an element of coherent sheaves on the diagonal, you will get F back after pushing forward. You will get something in the middle, which is the P1 lower star of P2 upper star of F tensor with O of 2 delta. And then you will get, again, F back. And by definition, you will get the cotangent sheaf. In this case, X is being a smooth variety, so cotangent bundle, in fact, of X, tensor with F. And again, this pullback push forward construction would be left exact because the modules that I have put in short exact sequence A are, you know, locally free OX cross X modules. Okay, so we have that. And now, what is this thing, by the way? This is, many are familiar with this thing, notationally at least. Sometimes they write it as J1 of F. So this is what? This is sheaf of first jets associated to this coherent sheaf F. That's it, simple. Sorry that I'm seeing, you know, I produce these dots on my iPad. So there's some glitch with my, with this iPad, and so I produce dots as I put my hand on the iPad screen, produces these dots. Anyway, I keep deleting them whenever they appear. Okay, so what does this then say? So I have this short exact sequence. Now here is a definition for a sheaf of OX modules, OS modules like F, or a complex, an object in the draft category, or a complex of such sheaves. Okay, let's call this thing A prime, by the way. Complex of such sheaves on X, the class of extensions represented by this short exact sequence A prime is called the Atiyah class. Atiyah class of F. It is notationally written as Atiyah class of F, and it's an element of the group that parameterizes such short exact sequences. If you look at this short exact sequence, A prime, it is clearly given by extensions, first extensions of F and, you know, F comma F tensor cotangent bundle. So this is what it is. So you can think of this group over X. This is a group over X. You can think of it as a complex vector space, and Atiyah class is a point of this complex vector space. So, okay, so this is the formula for Atiyah class. It's a point in there, and it's a class represented by such extensions. But what else does it measure? So, in fact, so here is a remark. Atiyah class, the Atiyah class Atiyah of F is the only obstruction to existence of an algebraic connection on F. That is, if short exact sequence A prime, which I had in the previous page, splits, then we can have an algebraic connection on this sheaf F. So, okay, so let me write it again here. So we have this one, we have the first jet of F, and then we have F. This is the short exact sequence A prime. If this thing is splits, it means that there exists a map from here to here, such that when you compose back with this projection map, you get identity on F. And then, of course, if you have such a splitting, then you can produce a map. You can go to first jets, and then you can project onto this factor in here. So let's actually do it. So actually, we can do this thing locally. So note that. So if I have these two maps, P2, P1, I can pick some neighborhood, open affine, for instance, neighborhood inside X, and then note that P2 inverse provides a homomorphism. For P2 inverse provides a homomorphism from local U sections of F, coherent sheaf F. U is this open affine in X, to sections of the pullback of F or on X cross X. So this is going to be local sections of X times U, and then restricted to diagonal, right? Because F is a sheaf after all supported on the diagonal, and then this thing, O of 2 delta. And just think about it. I mean, just look at the construction we had. And the point is that you see very easily via projection formula, you can easily see that this is nothing but the same thing as the U sections of the push forward of the pullback. So this is the U sections of P lower 1 star of P2 upper star of F tensor O of 2 delta. And that was our original sheaf of first jets on F. So, okay, so as you can see, P2 inverse locally provides a map from sections of F to sections of the first sheaf of jets on F. Now, if I pick a splitting, so we are trying to say if the short exact sequence is split, then we have an algebraic connection. So if S is such an splitting, so if S is an OX linear splitting, okay, if it is an OX linear splitting of A prime, if that is the case, then we can have some kind of an operator. I call it connection nabla, and this is going to be S minus P2 inverse, and so it's going to produce a morphism from F to F tensor omega of X. It's just simply trying to say that if you have a morphism this way and the composition is identity on the sheaf F, then you can get a map. First map it to sheaf of first jets on F, and then map it, project it down onto F times omega. And as you can see, this is really very similar to connections that we have on vector bundles in differential geometry and things like that. Okay, so let me actually turn off the sound on my computer so that my emails don't bother you. Okay, so that's that. So this provides a connection, and hence Atiyah class of F which is going to be giving you the set of such non-trivial extensions of that short exact sequence A prime, is providing the obstruction to existence of nabla. Okay, so that's that. I hope that now this is okay. As I mentioned, you can here F could be really an element of the bounded derived category. So it's okay. You can define algebraic connection on a complex, really. Okay. Another thing I would like to say, so Atiyah class is a point in this vector space. But over X, but you know, from very simple kind of obvious mathematics constructions, this is the same thing as a group. It's isomorphic to homomorphisms in the bounded derived category of X of F and F tensor omega of X with a shift by 1 in the derived category. So you can really actually think of Atiyah class of F as a map. So this is nothing but morphisms, all possible morphisms from here to here, but in derived category with a shift. Okay, so that's what it is. And sometimes you can see this in the literature. So this is all of the things that I said are assuming that X is a smooth variety. What if X is singular? If X is singular, if X singular variety, you can actually repeat the same construction. And roughly speaking, really, you can replace everything. You can replace the cotangent sheaf with the, you know, cotangent complex of X. So that's what it is. So if you have X as a singular variety, the cotangent complex, you kind of embed, you can embed X in some ambient to smooth variety. And then you will get some complex, obviously. So you will have some complex whose degree 0 term is the cotangent bundle of the ambient to smooth variety. So this is in degree 0, restricted to your singular variety. And then there is a -1 term. That's the conormal sheaf of this embedding. So let's say this embedding has some ideal. So this is the conormal sheaf, and then it keeps going like that, and -2 and so on. And it could be infinitely many terms even. And so this complex that you will get in the derived category of X is the cotangent complex. And then, you know, Illuzi and many other people actually talked about it. For us, for today, we will only work with, for the purpose of calculations of invariant, we only work with truncation of the cotangent complex. Truncation of L dot of X at degrees bigger than equal to -1, meaning that, you know, we are just interested in these two pieces. If X is a singular variety, singular scheme, even the Lim-Mumford stack, this is how the cotangent complex looks like. If it's like a quotient stack or something like that, you know, it could have a term in degree 1 and so on. So I'm sure that many people know about these things. So we are not working with those kind of things, Artan stacks or quotient stacks or things like that. Okay. By the way, what I said is very rough, and I didn't even tell you the construction. So, but at least I can put the result. So in this, for X singular, we can define what this Atiyah class, we can define universal. It's called universal Atiyah class, universal truncated, meaning that cotangent complex is being truncated, Atiyah class of F. And, you know, it is basically just for any F in the bounded derived category of X. And this is written like this, universal Atiyah class of F. It's an element of here. And F is now derived tensor product with the truncation of the cotangent complex in degrees bigger than equal to -1. The universal Atiyah class, with or without truncation, is defined in the amazing paper of Daniel Huybrechts. So this construction is due to constructions of Daniel Huybrechts and Richard Thomas. I think it's one of the most important papers, at least for me it is. So in their paper in 2010. Oh, it involved some kind of construction, Fourier-Mukai type transform construction, and with a special kernel. And it was a map from the bounded derived category of X to itself, and then that could define the universal Atiyah class for any object in the derived category of X. Okay, so that's that. And then, okay, again, this thing is isomorphic as a group to the homomorphisms from F to F tensor cotangent complex shifted by 1. From now on, I'm not going to put everywhere the truncations, but please do assume that I am only working with the truncated Atiyah class. Okay, so that's the universal truncated Atiyah class. We can also have a notion of universal truncated, okay, relative Atiyah class. So this is the important point. Relative. We can have relative, define some notion of relative Atiyah class. So what is that? Again, it's a very, now that I am hiding all the detail of Hilbert-Thomas construction under the rug, you know, it could be very easy in fact. So if I have some situation like this, I have two varieties, X and Y, and with the projection maps, P1 and P2, okay? And let's say I have some element in the X times Y. So an element of the bounded derived category of X times Y. So yeah, I have some element up there, for instance. Then I can define a Atiyah class of this object of derived category in over X cross Y. So Atiyah class of F is again over X times Y is an element of the extension group F, then F comma, F tensor, derived tensor product, cotangent complex of X times Y. But then of course you know that cotangent complex of X times Y or this truncation is actually written. I mean, we don't use truncation at this point. We use the full cotangent complex, and then later, every time that we would like to work with truncated ones, we can later truncate it. So first, we don't truncate. So it's going to be P1 upper star of L dot of X, direct sum P2 upper star of L dot of Y. Okay, so of course we can do that, and then we can project, in fact, this we can project onto the second factor. So in fact, if I, if I take this guy and replace it in here, right, and then project onto the second factor, of course I get a map from X1 to another thing. So this induces a map. Let me just put it here. This projection onto the second factor induces a map to X1, F, comma, F tensor, derived tensor product, pullback of L dot of Y. But okay, this is maybe silly, but okay, it's a notation. Of course, L dot of Y, because the cotangent complex is really a split sum of L dot of X and L dot of Y, L dot of Y is in fact the same as L dot of X times Y relative to X, right? It sees the difference of L dot of X cross Y and L dot of X. So it's the cone between the two cotangent complexes. So you can call it the relative cotangent complex this way. So this is why we call this thing, as soon as you get this group, there is an element in here, universal Atiyah, truncated Atiyah class of F, for X cross Y relative to the thing whose cotangent complex you coned out or you modded out with. So this is what it is. It's an element of this group. Okay, so we can have a universal truncated relative Atiyah class. What's the application of this thing? Well, here's an example. So applications. Here's an example. So let, in my construction, Y to be M X gamma, which I'm going to define as this moduli space of coherent sheaves or elements in the bounded derived category. But for now, let's say it's an example. So actually, let me put an example. Coherent sheaves on X with fixed churn character. Churn character R, churn of F. I want to fix it to be this vector gamma in the cohomology theory of the underlying variety X. Okay, then, what is then? I have a moduli space now, and let's like that. And this thing is something that, for those people who are familiar with moduli theories, they have seen this diagram really many times. And let us assume that M comes with a universal sheaf. So there is a universal sheaf in here, lives in the bounded derived category of X times M. And okay, now you can, for this universal sheaf, you can actually define the notion of universal Atiyah class. So here's the universal truncated relative Atiyah class of F with respect to X is an element of X1, universal sheaf times pullback of the cotangent complex of the moduli space. Well, you know, maybe up to some truncations that maybe later we can use. Okay, so that's that. Okay, so we have all of these things, and why is it even useful? So now I should tell you why am I interested in Atiyah class? Why interested in universal Atiyah class? In universal relative Atiyah class of this universal. Let us stick to this very example that I have a moduli space which is assumed to come with a universal sheaf, because this is what I'm going to talk about. Invariants and, you know, moduli spaces that produce my invariants often come with universal sheaves under certain assumptions that I fixed from the beginning. So let us just see what is this group actually gonna give us. So let us you know, focus on this thing and play with it a little bit. Again, silly thing calculation. So this thing, as we mentioned, is isomorphic to homomorphisms in the bounded derived category of X times M of universal sheaf and universal sheaf tensor with pullback of the cotangent complex of our moduli space shifted by one. Okay, so then what we can do in any book that describes, you know, it teaches derived categories, you can see that this group in the derived category is in fact isomorphic to another group. So it is the isomorphic to the group of, I can put this sheaf over here in this coordinate. So this will be an R hum, F tilde, F tilde. So it is the complex that is fiber-wise over every point of the moduli space captures self-extensions to all degrees of the sheaf that the moduli space parameterizes. And then I will be left with pullback of the cotangent complex of the moduli space with a shift. Okay. Now you can use Verdier, Grothendieck-Verdier duality. Grothendieck-Verdier. The amazing book of Daniel Hoybrecht's Fourier-Mukai transforms in algebraic geometry is one of the places that all of these statements, and he gives short courses on derived categories, and this is just fantastic. So for those of you, if you're a student and you haven't seen it, that's a really nice place to look at these. That's where I learned these kind of things. Okay, so this is how, and then Grothendieck-Verdier duality gives you a mechanism to go down onto M. So you can actually, this becomes again a isomorphic to a group of homomorphisms. This time I'm pushing forward onto M. So I think I change things. So it's going to be the higher direct image, higher direct push forward, higher direct image of this R hum complex. F tilde, F tilde. And then, you know, Grothendieck-Verdier duality always comes with a twist. So it's a twist in the derived category with dualizing complex of the projection, if it exists. So P2 with a shift D, and then L dot of M shifted by 1. And what is D? Let us assume that D is the complex dimension of X. So as you can see, the relative dualizing complex, I mean, we are looking at this thing. So let's say this is dimension, this guy is dimension of X, D plus dimension of M, and this thing is just has a dimension, right? So the relative dimension of this morphism P2 is D. And when you use the Grothendieck-Verdier duality, the Grothendieck-Verdier duality sees this twist by dualizing complex with the shift given by the relative dimension, and that's the dimension of X here. Okay, but what is the point of all of this? The point really is that I wanted to get to this point that I get the morphism from this term, all this term here, to the cotangent complex, and this is highly important for me. So this morphism is R P2 lower star R hum F tilde F tilde a tensor with the dualizing complex of P2. I can put all the shift on one side, D minus 1, and then cotangent complex. So it's highly important, this morphism, because this is the way to get invariants, really. So let's give this map this morphism a name, phi of x. Okay, so let us go to the next. So I have phi of x. This is the problem with the small pages, so I need to reproduce things. P2, D minus 1, L dot of M. Okay, so if first of all, if you look at fibers, this is some, this is some group on the whole moduli space. Arham is, it's something in the bounded derived category of x times m. Sheaf f tilde is the universal sheaf. You look at the fibers of f tilde over every point of the moduli space, it gives you one of those coherent sheaves on x. So if you look at fiber-wise over the points of the moduli space, this is kind of parameterizing all extensions, right? This is some kind of parameterizations of extensions of f really, I mean, without a tilde, because I'm looking fiber-wise. So fiber-wise, this is basically parameterizing these things. But also it could be that it's coming with this kind of, dualizing complex, which if the x is, smooth variety and so on, could be canonical bundle of x. So, okay, so I can, let's say, canonical bundle of x. So this is what it does. So it has Ham f and then x1s and x2 and x3 depending on dimensions. Okay, but the point is that after investigation, you can realize that this morphism in the derived category to the cotangent complex satisfies some interesting properties. So if you look at the induced morphisms on the level of cohomologies, sheaf cohomologies of these two complexes, you realize that H0 of phi of y is an isomorphism. And H minus 1 of phi of y is an epimorphism in this situation. And so this is just somehow from, telling you that this H0 of phi of y is actually, fiber-wise over every point of the moduli space parameterizes for you deformations of the points of the moduli space, which are here sheaves. And this thing is the obstructions. Okay, so it is something nice. It captures deformations and obstructions of points that the moduli space parameterizes, and these points are coherent sheaves on the original variety. This is why, hence, phi of x, the map, not just the complex, but the complex together with the map to the cotangent complex, is called deformation obstruction theory. Not necessarily perfect. So for those of you familiar with perfect obstruction theories, it means that you're looking at certain object on the derived category of the moduli space that parameterizes deformations and obstructions to deformations, but doesn't have any higher cohomologies. We are not saying that in here. It might be that there's obstructions to obstructions, and those are given by higher X groups. If you're lucky, you can have a perfect deformation obstruction theory. If you're not lucky, at least you can call it a deformation obstruction theory. Okay, so let me now say a little bit about these deformation obstruction theories. So deformation obstruction theories. So there are some amazing results. So first result is that when D, dimension of X, when D is equal to 3, Richard Thomas in his amazing work and thesis, let's actually give it some name. So this let's call this complex E dot of X. Okay. So there's a map from E dot of X to cotangent complex. So showed that E dot of X gives perfect deformation obstruction theory, meaning that there are no higher cohomologies beyond first order obstructions, but under certain conditions. And that condition was that when determinant of sheaves that the moduli space parameterizes is fixed. Okay, so that's what he showed. And then there is another result, which is Hilbert-Thomas in the same paper, which is the base of all of these constructions. They actually relaxed some of those needed conditions a little bit. So they showed that if the kernel of the canonical morphism, this is a canonical morphism. You can take self-extensions of sheaves that the moduli space parameterizes, and then you can apply the trace map to it, and you will get hi of O of x. Where is this really coming from? Well, the trace map really means that you can take the determinant of these sheaves. So there is a map from here to xi of determinant of the sheaves. These are coherent sheaves. And then you can take the determinant in this factor too. These determinants are invertible sheaves, line bundles. So they cancel each other and they produce this hi of Ox. So there's a canonical trace map, and this map has a kernel. So if the kernel of this canonical trace map vanishes, for I bigger than or equal to 3, okay, so what is it that we are doing? This is here. We are talking about this I here. If the kernel, by the way, this kernel, many of you are familiar with this. This kernel is nothing but the trace-free part of X, right? Because I'm taking the trace, the kernel of it is the trace-free part. So this kernel is basically the trace-free self-extensions of F, basically. So if this trace-free extensions vanish, okay, for I bigger than or equal to 3, then the complex, then phi of x, the map from E dot of x to L dot of m actually gives a perfect deformation obstruction theory. Okay, this is really fantastic. And after this, it helped a lot because, you know, people were thinking that Donaldson-Thomas theories only could be constructed on Calabi Yau varieties, and so we don't need these kind of things. You really don't need these kind of things. Okay, so one little kind of because it's related to my talk in here. Let me tell you, what if D complex dimension of the underlying variety is equal to 4. So fourfolds. What happens then? Then you have this phi of x, E dot of x to L dot of m. And then fiber-wise, you can see that fiber-wise funny things happen. So if you look at fiber-wise cohomologies of induced by the sheaf cohomology of E dot of x, you can see that, well, here are the cohomologies. So this E dot of x produces homomorphisms, endomorphisms of f, and then there is x1, self extensions of f of degree 1, and then there is x2, and then there is x3, and then there is x4. Okay, so there are so many cohomologies really here. Let us make even assumptions that we are only assume we are in Calabi Yau 4 situation. So X is a Calabi Yau 4. Its canonical bundle is trivial. We have self-duality. Let us assume that F is a stable sheaves. So, you know, they don't have non-trivial. To some extent, okay, so their endomorphisms are just C, right? C star or C. And then we can use the Serre duality, and these things do not jump because F is stable. Okay, so even though these cohomologies are there, we can ignore them because these things don't jump. The point is that in complex dimension 4, in comparison with complex dimension 3, so in dimension 3, we are in a very lucky situation because you have x1, x2, and x3. That's it. If you're assuming that you are in the, Calabi Yau situation, you can ignore these things, and then you see you have a complex E dot of X, which fiber-wise over every point of the moduli space has only two non-vanishing cohomologies. One of them is literally from Hartshorne deformation theory, deformation space, and the other one first-order obstructions. But here you have deformations. In the fourfold situation, you have deformations, obstructions, and obstructions to obstructions. So it's a three-term complex, and you cannot just easily construct virtual cycles based on constructions of Behrend and Fontecchi and other constructions. So it's a non-perfect deformation obstruction theory because of the dimension of underlying variety being 4. Okay, so this was the start of an amazing activity in enumerative geometry where people were trying to construct virtual cycles for those deformation obstruction complexes which have this situation, which are non-perfect. One of the recipes was the following. So if you have a situation where this X2 can be written as sum of some real, so here real, half-dimensional isotropic subspace. Isotropic subspace of X2. You see, X2 is written as a sum of two terms, and we want these two terms to be real half-dimensional isotropic subspaces. And you can see that it depends really on the problem. But if you can see that X2 can be written as V plus V dual, really, it should be V dual. Okay? Then something nice happens because you can see that via Serre duality, you can compare via Serre duality these pieces. So you can see that X1 and X3 are dual to each other by Serre duality. V and V dual are obviously dual to each other because X2 is self-dual, right? So then you can actually see that essentially this complex E dot of X, which has these non-trivial three cohomologies, really effectively is not so bad because half of it is what we need, because half of it is X1 and V. The other half is really the dual to X1 and V. The dual of X1 is X3. The dual of V is V dual. So effectively, it really is still a complex with two non-vanishing, non-trivial cohomologies. So using this then, maybe I can say it this way, and I'm sorry that I'm being very, very sloppy in here because I don't want to go through the detail. That's not the point of my talk. So this induces a local Korenishi structure. And a local virtual cycle. So you see, Korenishi theory is about deformation space and obstruction space. Here, your deformation space is X1, and your obstruction space, or the sheaf of obstructions, is half of the sheaf of obstructions, X2, is V. So, okay, with these two non-vanishing obstruction sheaves, you can construct locally virtual cycles following the Behrend and Fontecchi construction. But then the point is that in order to glue, so remark, in order to glue these cycles, these local cycles, well, we need to consider the moduli space. Moduli space is moduli space M with its homotopical structures, with its homotopical structure. Okay, so in some sense, I'm trying to say that, you know, you need to really use derived algebraic geometry. So derived algebraic geometry. So basically, you need to go to some ambient derived moduli space that contains your original moduli space and construct a virtual cycle derived analytically there, basically. And then for construction of that virtual cycle, you will use a lot of homotopical structure of the ambient derived moduli space. So who are the people who worked on these things? In fact, let me say something. Looking at this half of the obstruction sheaf, I think, to my understanding, really, I think originally this idea also was coming from Richard Thomas. So first of all, in terms of exposition of material, I should say ideas were initiated by Thomas and Donaldson. They had a really amazing paper in the higher dimensional gauge theory or something like that. And I think ideas were already there. But anyways, effectively, long time after, Conan Lung and his student Sao actually constructed these virtual cycles for Calabi Yau, for geometries, for the moduli space of vector bundles, for moduli space of vector bundles. Okay, and then, well, you know, this was really amazing, but often it is the case that you have a vector bundle, you deform it, it's not gonna really stay as a bundle. So that's why the activity actually further continued. Dominic Joyce and his group, and especially Dominic Joyce and collaborators Chris Brav, who is in Moscow right now, and Denis Borisov, who I had the pleasure of working with for a while. These people also worked it out, not for just vector bundles, but actually for sheaves. So they constructed real virtual cycles on the moduli space, on moduli spaces of sheaves, not just bundles, but actually sheaves, using derived, maybe it's better to call it derived differential geometry. Okay, so that's that. And then there is a really interesting thing recently. So I will put this in red because it was kind of very exciting for me. So new result is result of, if I'm putting the name correctly, Jung-Sok Oh and Richard Thomas recently constructed an algebraic, not real, algebraic virtual cycle using, if I'm not mistaken, using localization, some technology, localization of Edidin Graham's square root Euler classes. Euler class for SORC bundles. Okay, so some construction. They also showed that their invariance. So after you construct these virtual cycles, you can integrate certain appropriate cohomology classes against virtual cycles, and you can obtain invariance. So they showed that their invariance match with Borisov-Joyce invariance. Oops. Okay, my pen is not writing. Borisov-Joyce. Okay. All right. So this is that, but it's 10:52. Okay, so at least in Boston. So I will go and tell you a little bit about certain moduli space of sheaves and Calabi Yau fourfolds, for which we don't need derived algebraic geometry. So today, a special case, I would like to just mention a special case for today. We do, let's say I have a variety Y, smooth and projective, and I have another variety X, which is given by total space of canonical bundle of this variety Y. So, okay, so I have a non-compact variety X, including having variety Y as the base of zero section of a canonical bundle of it. Okay, and let's say I have an embedding of the zero section inside X, I call it I, And let's say dimension of X over complex numbers, some number D. Okay, let us assume that I have a moduli space. So this is the moduli space of sheaves on compactly supported sheaves on X. So this means really compactly supported sheaves on X that have proper support on Y. So okay, let's say I have a moduli space like this, and let us assume that sheaves F are scheme theoretically supported on Y. Okay, not only they are set theoretically supported on Y, but scheme theoretically supported on Y. So for instance, if you're doing curves, let's say, if you have a Y whose normal bundle inside X is negative, the curve cannot thicken out from Y into X. If you look at the structure sheaf of these things, these are just all Y modules, and these are scheme theoretically supported on Y. So this is a situation we are interested in. Okay, so here's a remark. What is the point of this thing really? So remark, first of all, scheme theoretic support on Y actually implies that for any sheaf in this moduli space, then I can write that sheaf is isomorphic to push forward of some sheaf G, where G is an element of coherent sheaves on Y. Anything that I pick inside this moduli space F is going to be a push forward of something coming from Y. Why? Because my assumption is that F's are scheme theoretically supported on Y. Okay, so then what is the point? So we can think of this moduli space as a moduli space of sheaves on X with a scheme theoretic support on Y, or we can think of moduli space of OY modules, moduli space of sheaves G given as OY modules. And these two moduli spaces are really the same, equal moduli spaces. Okay, but what is the point? The point is that yet we can associate. So let us call this thing as a whole M. We can associate to M two different, completely different obstruction theories. And even though, this is the point, which is really interesting, even though F's are the same as G's pushed forward into the ambient non-compact variety X, deformation theory of these F's and G's are different from one another. So let's actually look at it. So let's look at this situation. So I have X times M. Let's say I have a universal sheaf F on it. And then I have Y times M, and I have the universal sheaf G on it. There is an embedding I tilde, because Y is being embedded as in X as the zero section. There's an embedding of Y times M into X times M. And then universal sheaf is isomorphic to push forward of the universal sheaf G. And let's say I have, projection maps onto X, projection map onto Y, and this is Y and X. And then I have projection map onto M, and I have projection map onto M, and these two maps are equal. Same moduli space, really. Okay, so what is the point? So now I can construct two different obstruction theories. So for this, let's call these things P and P prime. So for P, I can construct a morphism. So R, P lower star, the thing that I just constructed, R ham, F tilde, tensor with the dualizing complex of the relative morphism P shifted by D minus 1. And it gets mapped to the cotangent complex of the moduli space. Maybe I can be interested in the truncation of these things, right? And for y also, for the p prime, so this is coming from this morphism here, and then I would like to do the same thing in here. So let's write that one down too. It is some theory associated to y, so I call it phi of x. And then I p prime lower star, r universal sheaf G, tensor with dualizing complex, relative dualizing complex, the morphism p prime. Well, y is dimension 1 less than dimension of x, right? So this is clear that it's going to be d minus 2. And same thing, L dot of m, because the two moduli are the same. Okay, yet phi x and phi of y are different. In fact, phi of x is not equal to phi of y. And this is really because the derived category doesn't see that they are capturing deformations and obstructions of the same object. So let's see why that is the case. Why? So let's do some fiber-wise analysis. So fiber-wise analysis. Vanya, can I ask you, how much time do I have if I want to take a little bit more time?
It's absolutely okay because you started late.
Ah, okay. Okay, thanks so much. Okay, so let's do some fiber-wise analysis and compare what, actually, let's give these things some name. So let us call this thing, as I called it before, E dot of x. And let us call this thing, as I called it before, E dot of y. I would like to see if there is any difference between E dot of x and E dot of y, any non-vanishing difference, any discrepancy between them. Okay, so let's see how I can see that. Fiber-wise, E dot of x captures self-extensions of f comma f, maybe modulo some twist by the canonical bundle of x. And fiber-wise, E dot of y captures self-extensions of g, twisted by canonical bundle of y. Okay. Okay, so let's just see. What I can do is to see how they are different from one another. I can do some game. So what I can do is I can take one of those g's. So take one of these sheaves g, push it forward into the ambient variety. So G is an OY module. I'm pushing it forward into non-compact X and then pulling it back. That's it. Pull back because it has to do with tensoring with the structure sheaf of Y, right? And Y is codimension 1 is the drive tensor product. That's why I'm drive pulling back. So what do I get? I will get G back, but then I will get a discrepancy, actually, which is G tensor conormal bundle of Y inside X with a shift in 1. So this is due to, this is an exact triangle. Exact triangle in bounded derived category of Y. This exact triangle was investigated and shown to hold true by Bondal and Orloff. Okay, and since Y is the zero section of X given by total space of canonical bundle, so it's a zero section of a bundle, then in fact this exact triangle is splits really. So it's a split exact triangle. Okay, so it is splits. And then let's just see, still I don't want to write it as G plus G tensor. And why? Because it's easier to look at it in this way, even though we know that it is split. So let us apply some operator to this thing. So let us apply R hum blank G to this exact split exact triangle. So what do we get? We will get, starts from the right hand side. So R hum G comma G. We will get R hum pull back or push forward of G comma G, right? And then we will get the other thing, R hum G tensor. Well, so normal bundle of Y inside X is a line bundle because Y is codimension 1 and this line bundle is invertible. So I can put it on the other side. So let's do that. So G comma G tensor normal bundle of Y in X, oops, and then shift, well, shifted by -1, right? The shift goes to the other side and becomes -1. Okay, but why is this useful? Because in fact, you can use the left adjoinance of the derived pullback and push forward to see that this is nothing but Arham I lower star of G, I lower star of G. But Arham I lower star of G is what? It's F over there. So I can just think of these as Fs. Okay, so this is very nice. As you can see, the object in the middle of the exact triangle, a split exact triangle we get, captures its cohomologies, sheaf cohomologies captures deformations of the sheaf F. The object on the left-hand side has cohomologies which captures deformations and obstructions of the sheaf G. But there is something non-vanishing on the right-hand side, which captures the part of the cohomologies or obstructions of F, which are induced by normal bundle of Y inside X, meaning that part that is induced by deformations of Y inside X. Even if the normal bundle of Y inside X is negative bundle, it's true that you might not have homomorphism, but you might have extensions, X1, X2. So this term that you get on the right-hand side is non-trivial, really, in general. So let's call this term something. So clearly, of course, you see this phi of X here and phi of Y here. These are made of Arham F comma F and Arham G comma G modulo some twist and shift in the derived category. So the reason I'm working with this exact sequence, exact triangle in here is that you can clearly see that after twisting by omega and maybe shifting and so on, there is a discrepancy between E dot of X and E dot of Y too, which is induced by what I just showed in the bottom of the page. So, and what is in the bottom of the page is a split exact triangle. So, okay, so this in fact implies that we get, this implies that we get, in fact, E dot of X becomes isomorphic in the derived category to E dot of Y plus a discrepancy, D dot, which sees the difference of Y inside X, difference of deformations induced by deformation of Y inside X. And this thing is actually Arham G comma G tensor normal bundle of Y inside X shifted by D minus 2. And maybe modulo some twist, something like that. Okay. So this is what it is. So as you can see, even though the moduli spaces are the same, G's are the same as F's, derived category is blind with respect to this. So it still produces non-vanishing cohomologies. And okay, remember that from E dot of X and E dot of Y, you're constructing virtual cycles out of the cohomologies induced by these objects in the derived category. So then, of course, it becomes very curious. Is it that the invariants are different then? But it's the same moduli space with two different obstruction theories. Are the invariants different or not? And so this is something that my collaborators and I were very interested to investigate. So here's a theorem. Diaconescu, Emmanuel Diaconescu at Rutgers, myself and Professor Yau in 2018. This paper got published, so you can find it now in Advances. So here's a theorem. Consider universal. I write the theorem and then I explain it. Universal Atiyah classes, and by these I really mean truncated Atiyah classes. Atiyah classes. So universal truncated relative Atiyah class X times M over X of universal sheaf F, which is an element of Arham bounded derived category of X times M, F tilde with P upper star of L dot of M, shifted by 1. And then universal Atiyah class for the other one, so sheaf G, universal sheaf G, Y times M relative to Y, which is an element of Arham dB of Y times M, G tilde tensor, derived tensor product, P prime upper star of L times M. Okay, so these are the universal Atiyah classes. If you consider these things, then let's call this complex in here B dot of X times M relative to X. Let's call this complex in here B dot of y times m relative to y. So Atiyah class is a point of these groups. Remember, it's not equal. It's always a point of these groups. This is why I need to give these different names. So then there exists, the theorem says there exists, as I showed you, there exists a decomposition. There exists a decomposition. B dot of x times m over x is equal to I tilde lower star of B dot of y times m over y plus some term, which is I lower star of r ham G tilde tensor with P upper star of canonical bundle of y, and then G tilde tensor with L dot of m shifted by 1. Some discrepancy term there. And with respect to this decomposition, such that with respect to this decomposition, we can see that in the level of Atiyah classes, this is what happens. Universal Atiyah class of F becomes equal to universal Atiyah class of G, comma 0. So even though, so I put it somewhere, I want it to be on the same page. So you see, you have E dot of X, we showed it, it becomes E dot of Y plus the discrepancy term. Okay, universal Atiyah class based on those consequences of, chain of isomorphisms that was using the Verdier duality actually shows you that if you start from B dot, or if you start from B dot of Y, you can follow those isomorphisms, and those induce for you groups that give you morphisms from E dot of X to the cotangent complex and from E dot of Y to the cotangent complex. So this is actually induced by B dot of X times Y, M, and this is induced by B dot of Y times M over Y. Okay, and so the question is, what happens to this other thing? So there is also a map from here to here. What happens? And the point of our theorem was that when you chase the point inside these groups, there is a point in here, P, and that point falls inside this factor, P. P falls inside this factor, but it doesn't see that the other factor. So even though the derived category is blind with respect to the fact that we are looking at the same moduli space, still in the level of Atiyah classes and the virtual cycles induced by these Atiyah classes, we can see that Atiyah classes are the same, therefore the virtual cycles induced by them are also the same. So what's the corollary of this construction? So let me go to one of the original slides and delete it. So how should I? Clear. Okay, corollary of this construction is that a virtual cycle induced by, virtual cycle induced by the morphism from E dot of X to the cotangent complex on this moduli space is equal to the virtual cycle induced by phi of Y, even though the derived category is blind with respect to moduli spaces of G and F being the same exact thing. Okay. Therefore, when you do integration of some appropriate cohomology classes against these virtual cycles, you can see that the Donaldson-Thomas invariants of sheaves on X with the fixed Chern character on the fourfold become equal, in fact, to Donaldson-Thomas invariants of sheaves with the same Chern character as OY modules, threefold. So this is one of those examples that we are in really lucky situations that, okay, seems like integration against virtual cycles of fourfold moduli space is hard, but no, well, we just need to do the usual threefold, deformation, DT theory. Really. So what's the application finally? The application is here. So I just mentioned very quickly. So let S be a smooth projective variety, the projective surface, and we constructed two theories. So one of them, so let's say there is a and D inside S an effective divisor. Effective divisor in this projective surface. So we construct from this surface a fourfold and a threefold. So let's say X is total space of canonical bundle of the algebraic surface twisted by this effective divisor in S plus O of S minus T. This is a rank 2 bundle on the projective surface, so it's a fourfold. And we can have sitting inside it a rank a threefold, which is just this piece X ks of D going to S. So this is a threefold. And the reason we were interested in these things is that these things have applications in theoretical physics and so on. So we fix some sheaf in compactly supported category of compactly supported sheaves on X, whose Chern character with Chern character of the sheaf F to be some vector which is given by 0, 0, 2 times class of the surface, some kind of codimension 2 sheaf. So I have a surface S, I have some rank 2 bundle L1 plus L2. I'm looking at sheaves which are supported on the surface. These are codimension 2. But of course there is inside it, if you just ignore one of the factors of L's, one of those line bundles, there is also this non-compact threefold. And these sheaves are also compactly supported sheaves on that threefold. So okay, so we are looking at those particular sheaves, codimension 2 sheaves with set theoretical support on S with this given Chern character. We showed that dt of X is equal to dt of Y. You see, it's a fourfold dt theory inside X. It's very interesting. But it's also the threefold dt theory when I realize these sheaves inside Y. There's another thing that our sheaves in this particular example are set theoretical support on S. They are not scheme theoretic. But you can actually see that because of the negative bundle in here, they are scheme theoretically compactly supported on Y, meaning they can deform into Y, but they cannot deform into X. Okay, so that's it. And then we actually showed that these invariants of fourfold are the same as invariants that in the level of the threefold that we can calculate. And because of the particular choice of Chern character, there are so many results on these invariants. So Tanaka and Thomas studied these things. And so they actually showed, we showed, okay, anyways, so how should I say it? So there was a result of us, Golampur, myself, and Yau, that studied in particular this threefold theory version of these sheaves. And we showed that invariants dty of threefold are equal to invariants that Tanaka-Thomas defined. And what are those invariants? Those are mathematical definition, mathematical Tanaka-Thomas invariants, let's call them invariants. Those are mathematical definition, in fact, of virtual count of points in moduli space of solutions to Waffle-Witten equations. So very important physical equations, very, very important physical theory. So in fact, Tanaka-Thomas mathematically were the first people who defined what is Waffle-Witten invariant mean, really. And they did some kind of really kind of interesting construction of a virtual cycle for the moduli space of solutions to Waffle-Witten equations. And then somehow independently, we were working on a non-compact threefold theory with the compactly supported sheaves on a surface. And via localization, we realized our invariants match up to some equivariant parameters with Tanaka-Thomas invariants. So our invariants also match with Waffle-Witten invariants, luckily. Okay, final thing I'm gonna put, and then I will really stop, and sorry I'm taking so much of your time, is this. So just the fact is that these Waffle-Witten invariants on X are going to be, we showed that they're going to be equal to Seiberg-Witten invariants. Invariance of S twisted by some combinatorial coefficients, plus correction terms, which are really invariants of what we called nested Hilbert schemes. nested Hilbert schemes. And these are, like, if you have as nested Hilbert schemes, are things that moduli spaces that parameterize non-pure, meaning one-dimensional and less sub-dimensional sub schemes of the variety. So configurations of nested configurations of points and curves inside this X, and they could have general length, not just length 2, but it could be like that. So these nested Hilbert scheme, they have invariants, and those are the correction terms that you need to add to a twist of Seiberg-Witten invariance of X by some combinatorial coefficients, and you will get Vafa-Witten invariance of X. And Vafa-Witten invariance of X are equal to these threefold DT invariance of Y. And even though actually Y, okay, and even though we are looking at a, fourfold theory, still these fourfold invariants are equal to those. So this is final results, and I just stop here. So sorry for, going over time. Thanks.
Okay, thank you, Artan. Let's thank the speaker. Okay, questions?
I could have a naive question.
Yes.
Absolutely.
So, you're computing in this particular case where X is the total space of a canonical bundle over threefold, the T-type invariance. I was so you said in generality this Joyce Borisov or Richard Thomas construction, this algebraic complicated construction computes them. And in this particular case, you use this Atiyah class to compute them. So are you proving that this Atiyah class construction used to describe virtual class and so on agrees with the Borisov-Joyce construction?
No, not in general. Our Atiyah class construction here is basically telling us that our virtual cycle is the threefold virtual cycle. So yes, Joyce's construction in case of the non-compact threefold, if you localize their virtual cycle, should agree with this. But ours is much more specific than theirs.
I see.
So for instance, if the Calabi Yau fourfold is compact, ours doesn't work.
Okay, thank you.
Yeah, sure.
Thank you, Artan. I have small questions. So can you do the similar constructions for log Calabi Yau with boundaries?
A very good question. We are working on it. Yes,
Okay, it's now trendy to do everything in the log.
Yeah, I think so.
Okay, good.
But you need to define log DTs, log sheaves, and you can have some notion of parabolic sheaves. So when you have the logarithmic scheme with the variety together with the choice of the divisor, then that logarithmic structure induces some logarithmic structure on your sheaves. Logarithmic structure on your sheaves is some kind of choice of a parabolic filtration of your sheaves as they get close to the divisors. And so you should look at the moduli space of log sheaves. And you can, yeah.
Okay. Any other questions to Artan? Okay, if no, let's thank Artan again. Thank you.
Thanks so much for having me.
Thank you very much. And I stop recording.
Cheers.
Okay. Okay.